Students, today we are going to discuss NMR spectroscopy and also PSR spectroscopy. In yesterday's class, we have discussed MOSBY spectroscopy. So, let us start the class. I'll share the screen. So, here, what is spectroscopy actually? Spectroscopy is a study of interaction of EMR, electromagnetic radiation with matter, which may result in absorption, transmission, emission, reflection, or rotation of EMR. So, whenever an electromagnetic radiation will interact with any matter, with any sample, the sample may absorb the EMR, that is electromagnetic radiation, or else it may transmit through it, or else it may emit, or else it may reflect, or the sample may rotate. Okay, so the study of that is called the spectroscopy. Okay? Nuclear magnetic resonance spectroscopy, most commonly known as NMR spectroscopy. So, nuclear magnetic resonance. Here, N stands for nuclear, M stands for magnetic, and R stands for resonance. So, nuclear magnetic resonance spectroscopy is known as NMR spectroscopy. Okay. So, NMR spectroscopy, that is nuclear magnetic resonance, is a spectroscopy technique which is based on the absorption of electromagnetic radiation. So, whenever the electromagnetic radiation falls on the sample, it may absorb, or it may transmit, or it may reflect, or it may rotate, right? So, when the sample absorbs the light, this NMR spectroscopy, NMR will occur. Okay, nuclear magnetic resonance is based on the absorption. Okay, NMR spectroscopy is based on the absorption of electromagnetic radiation. Okay, if it is scatters, it is Raman spectroscopy. So, absorption spectroscopy is also, uh, we can say absorption spectroscopy is a nuclear magnetic resonance spectroscopy. IR is also an absorption spectroscopy. Okay, nuclear magnetic resonance spectroscopy is a technique absorption of which is based on the absorption of electromagnetic radiation in the radio frequency range of 4 to 900 megahertz by nuclei of atom. So, in what range it will vary? This radio frequency range is from 4 to 900 megahertz. Okay, the absorption of electromagnetic radiation occurs in the nuclear magnetic resonance spectroscopy, which is based, NMR is based on this absorption spectrum. So, the radio frequency, it occurs in the radio frequency range of 4 to 900 megahertz. Okay. Proton nuclear magnetic resonance spectroscopy, PNMR, we will say proton magnetic resonance spectroscopy is one of the most powerful tools for elucidating the number of hydrogens or proton in the compound. So, this proton nuclear magnetic resonance spectroscopy is a powerful tool for elucidating the number of protons or number of hydrogens in the compound. If you want to find the number of protons and number of hydrogens in the compound, we will use this proton nuclear magnetic resonance spectroscopy. Okay. Spectroscopy determines the physical and chemical properties of atoms or the molecules in which they are contained, and provide detailed information about the structure, dynamics, reaction state, and chemical environment of molecules. So This spectroscopy, what it determines? It determines the physical and chemical properties of atoms or molecules. Okay. This spectroscopy will be used to determine the physical and chemical properties of atoms or molecules. So, which are contained detailed information about the structure. So, this physical chemical properties contains this structure information about the structure and dynamics, and also reaction state and chemical environment of the molecule, where the molecule, how the chemical environment of the molecule is present, and what is the structure of the molecule, and what are the dynamics which are there, and what is the reaction state, we can find using this spectroscopy technique. Okay. It is used to study a wide variety of nuclei. So this spectroscopy is used to study the wide variety of nuclei. Here 1H hydrogen, 1 hydrogen and 15 nitrogen, that is mass number. Okay. So fluorine 19, carbon 13, potassium, sorry, phosphorus 13. So P13. So theory of NM. Spin quantum number I is related to the atomic and mass number of nucleus. So spin quantum number I will be related to the atomic mass number. Okay, atomic mass number of nucleus. So, so the spin which are having half spin or integral spin only can be used for this NMR spectroscopy. So spin quantum number I is related to the atomic and mass number of nuclei. Atomic number is nothing but number of protons, and mass number is nothing but number of protons plus neutrons. So I will be, spin quantum number will be half integer when atomic number is odd. So atomic number of atomic number and mass number are odd. If atomic number is odd and mass number is odd, the spin will be half integer. Thus, we can find the nucleus spin. Okay. So actually, this NMR depends on the nucleus spin of the element. So atom, if the if it contains integral or if it contains the spin, then only it contains the magnetic moment. So the elements which contains this spin, integral of half integral spins, can be used for the NM. So here half integral will be, how can we find the atomic spin, nucleus spin? Actually, we can we can find the nucleus spin by using this atomic number, by seeing the atomic number and mass number. If the atomic number and mass number are odd, then the integral spin will be half integral. The nucleus spin will be half integral. If the atomic number and mass number are even, both are even, then the nucleus spin is 0. Spin quantum number I is 0 here. Spin quantum number I is 0. So, when atomic number is odd and mass number is odd, there will be half integral. When atomic number is odd and mass number is even, then it is half integral. Then also it is half integral. When atomic number is even and mass number is odd, then it will be integral quantum number. That is, spin quantum number is integer. Okay. So we can see the example of 1 hydrogen, that is half spin. Then 13C carbon. You can see here, this is half spin, and here 2 hydrogen, that is integral spin, which is integer, and 0 when both are even, when mass number and atomic number is even, that is carbon 12. Okay, here the spin is 0. Okay, so elements with either odd mass or odd atomic number have the property of nucleus spin. So elements with odd mass number or odd atomic number have the property of nucleus spin. Either atomic number must be odd, or else mass number must be odd. So then only we can find the spin. Okay, nucleus spin. If an external magnetic field is applied, the number of possible orientations calculated by 2L plus 1. So here you can find, whenever external magnetic field is applied to those nucleus, what happens? Number of possible orientations can be calculated by using the formula 2l plus 1. We can find the, sorry, 2I plus 1. We can find the number of possible orientations. So this I indicates the spin quantum number, isn't it? Hydrogen has spin quantum number of I is equals to half, right? And the possible orientations will be 2 into half into plus 1, right? 2 into half into plus 1, that is 2. So number of orientations will be possible only 2, that is plus half and minus half. So whenever an external magnetic field is applied, the number of possible orientations can be calculated, orientations can be calculated by 2I plus 1. Where the, if you take an example of here carbon 13 also, there is half, right? I is half here, half integer. So 2I plus 1 is 2. There are two states of two states for the two orientations possible for the carbon also. Okay, carbon 13. So he has taken the hydrogen example here. That is I is equals to half and possible orientation will be 2, right? Plus half and minus half. If the magnetic field is applied like this, so in this direction, you can see one state is plus half state and another state is minus half state. So plus one plus half state, spin state and minus half spin state. So we can find the orientations by using this formula 2I plus 1. Okay. So principle of NMR. Let us see the principle of NMR. So the principle is based on the spinning of nucleus and generating the magnetic field. So the principle is based on the spinning of nucleus. Okay. How the nucleus spins and generating the magnetic field. Okay. Without external magnetic field, nuclear spin are random direction. So whenever there is no external magnetic field, the orientation of this nuclear spins will be random. Okay, the movement of these nuclear spins will be random. When you apply the magnetic field, with magnetic field, nuclei align themselves either with or against the field of external magnetic field. So actually this NMR principle is that it is based on what? Spinning of nucleus and generating a magnetic field. Even we can take an example of Earth also. It spins around, it spins with about its own axis. That's why it contains magnetic field, right? So spinning nucleus also generates the magnetic field here. We can take an example like that. So without external magnet, if there is no external magnetic field, the nucleus spins will be random like this. You can see here the spinning proton creates a magnetic field. So the proton which is spins can create a magnetic field here with no external magnetic field. We can observe here with no external magnetic field, the orientation of this, the movement of these protons are in different directions. You can see here the nuclear magnets are randomly oriented. But when B naught is applied, that external magnetic field is applied, either the nuclei align uh, against the field or towards the field, isn't it? The nuclear magnetic field is applied in this direction. So the movement is some of the spins are some of the protons are moving in this direction and some are against to the magnetic. You can observe here the nuclear magnets are oriented with or against magnetic field. So you can see here these are the states: ground state and excited states, high energy and low energy. So spins will occur whenever we will give the energy to the ground state uh, atoms. Okay. So if an external magnetic field is applied, an energy transfer is possible between ground state to excited state. So you can see here when external magnetic field is applied, an energy transfer is possible between ground state to excited states. Whenever we give the energy magnetic field, when we apply a magnetic field which are to the ground state, what happens? They will excite and go to try to go to the excited state, isn't it? So when the spin returns to its ground state level, the observed radio frequency energy is emitted at the same frequency level. When the spin returns to its ground state level, the observed radio frequency energy is emitted at the same frequency level. So the observed radio frequency which is taken by the ground state will be emitted with the same frequency level when it comes to the ground state. Okay. The emitted radio frequency signal that give NMR, the emitted radio frequency signal that give the NMR spectrum of the concerned nucleus and is directly proportional to the strength of the applied field. So the emission which is taken, which is given as radio frequency signal that gives the NMR spectrum. Okay, NMR spectrum of that concerned nucleus. So that NMR spectrum will be directly proportional to the strength of applied field. As the applied field is applied field will be directly proportional to the NMR spectrum. When NMR spectrum is high, we can observe the strength of the applied field is high. So this is the relative energy to increasing magnetic field strength graph you can observe here. So here when magnetic field is applied, M is equals to spin is equals to plus of magnetic spin is equals to minus of, where I is a here you can observe the spin quantum number, that is half. Okay, so these are the two states, plus of and minus of. Okay, that is we found that 2i plus 1 by using that formula we have seen here. The M is equals to plus of and M is equals to minus of. NMR spectrum. NMR spectrum is a plot of intensity of NMR signals versus magnetic field frequency in reference to TMS. The TMS is nothing but tetramethylsilane. So actually, always we will take the reference of this tetramethylsilane because it has some standard qualities, so that we will take as a reference. We take this as a reference and we will try to plot the graphs. Okay, NMR spectrum is a plot of intensity of NMR signals versus magnetic field frequency in reference to TMS. TMS is nothing but tetramethylsilane. Okay, here intensity to frequency is drawn. Here this is the downshield, this is the upshield. Okay, this is the downshield and this is the upshield. Here you can observe. So shielding nuclei, this is shielding nuclei, TMS. So here reasons for taking TMS as a reference standard is why we will take TMS, tetramethylsilane, as a reference means here you can see it is chemically inert. Okay, this TMS is tetramethylsilane is chemically inert, magnetically isotopic, volatile, and soluble in most organic compound solvents. Okay, PMS gives an intense signal. Okay, it gives the intense signal. PMS can be easily removed. So it can be easily removed because it is an inert one, which is chemically inert. Electronegativity is low. Here, the electronegativity will be low for the TMS. It doesn't make any intermolecular association with the sample. So as this is inert and it doesn't make any intermolecular association, and also it gives an intense signal, and also it can be easily removed. That's why TMS will be taken as a standard reference curve plot. Okay? Plot a curve. So intensity, plot of intensity of NMR signals versus magnetic field uh, is done by using, by reference, taking the reference as AMS. Okay, these are the reference standard reasons for the, for taking the TMS as reference. Okay. Next one is chemical shift. Here, chemical shift, if you see, is, it is the resonant frequency of nucleus relative to standard in a magnetic field. So chemical shift is the resonance frequency of a nucleus, which is the resonance frequency of nucleus relative to a standard in magnetic field. So TMS, tetramethylsilane, is the most common reference compound in NMR. So in NMR, we'll mostly use this TMS as a reference compound. Okay, TMS is the most common reference compound in NMR. It is set at delta is equals to 0 ppm. Okay, 0 ppm. So delta is equals to V sample minus V reference by V reference. We can find the delta, chromical delta difference. We can find. We can find the delta. So here 0 parts per. You can observe TMS is most common reference compound in NMR, which is set at delta is equals to 0 parts per million. Okay, delta is equals to V sample minus V reference. Okay, shielding of protons. Next is shielding of protons. High electron density around the nucleus shields the nucleus from the external magnetic field, and the signals are upfield in the NMR spectrum. High electron density around the nucleus shields and the nucleus from the external magnetic field. Okay, and the signals are upfield in the NMR spectrum. De-shielding of protons. Lower electron density around the nucleus de-shields. So low electron, here in the shielding of protons, high electron density around the nucleus shields. Here when de-shielding of protons will be taken as lower electron density around the nucleus de-shields. Okay, so from the external magnetic field, and the signals are downfield in the NMR spectrum. The signals will be downfield in the NMR spectrum. So this is the de-shielding and downfield, and this is the shielding and upfield. So ppm nothing but parts per million. So we can observe here. You can observe here. You can observe high electron density around the nucleus shields the nucleus from the external magnetic field, and low electron density around the nucleus shields the nucleus from the external magnetic field. So this gives the upfield of in the NMR spectrum. This gives the shielding of protons, gives the downfield field in the NMR spectrum. Okay. Factors affecting factors affecting factors affecting the chemical shift. So what are the factors which can affect the chemical shift? These are the factors: electronegative groups, inductive effect, magnetic anisotropy of pi systems, diamagnetic effect of pi bond, hydrogen bonding, van der Waals de-shielding, effect of temperature, effect of solvent. If you see, first one is what? Inductive effect or electronegative groups. So factors which may affect the chemical shift is, the first one is electronegative groups, which are the groups which are electronegative. Those can affect the chemical shift, and also diamagnetic effect of pi bond. Diamagnetic effect of pi bond also affect the chemical shift. Hydrogen bonding also may affect the chemical shift here. Van der Waals de-shielding. Van der Waals de-shielding also affects the chemical shift. Effect of temperature. If the temperature is more, or this changes, that also affects the chemical shift, and also of effect of the solvent which we are dissolving. Okay. So electronegative groups. electronegative groups. First effect which can affect the chemical shift is the electronegative groups. Electronegative groups attached to the CH system. Electronegative groups attached to the CH system decrease the electron density. So electronegative groups attached to the CH systems decrease the electron density around the protons, and there is less shielding, that is de-shielding, and chemical shift increases. So the electronegative groups which are bonded to this CH system decreases the electron density around the protons. There will be decrease in the electron density around the protons when the electronegative groups are attached to CH groups, and there will be de-shielding and chemical shift increases. So there will be de-shielding will be happens. Okay, these are the compounds, these are the chemical shift. You can observe the observe here. CH3I, this is CH3I, and this is CH3Br. These are electronegative groups, iodine, bromine, chlorine, fluorine. You can observe the chemical shift here. CH3 for CH3I, it is chemical shift is 2.16, and for CH3Br, the chemical shift is 2.65, and for CH3Cl, it is 3.10, and for CH3F, methyl chloride, that fluorine, you can observe 4.26 here. Okay, this is about the electronegative groups. And next one is magnetic anisotropy of pi systems. These are also affects the chemical shift. So you can see the magnetic anisotropy of pi systems or space effect, we will say. So magnetic anisotropy means that there is non-uniform magnetic field. So magnetic anisotropy means actually it is the non-uniform magnetic field. If the magnetic field is not uniform throughout the nucleus, then this may affect the chemical shift. Okay. So magnetic anisotropy means that there is non-uniform magnetic field. Electrons in pi system. Electrons in pi systems, example aromatics, alkenes, alkynes, carbonyls, etc. Electrons in pi systems, examples are aromatics, alkenes, alkynes, carbonyls, etc. interact with the applied field. So these will interact with the applied field, which induces a magnetic field that causes the anisotropy. So electrons in the pi systems, interact with the applied field. So the pi system electrons will interact the applied field, which generates a magnetic field that causes the anisotropy. So as the electrons interact with this applied field, what happens? There will be inducing of magnetic field occurs that causes the anisotropy or non-uniform magnetic field. Okay, it causes both shielding and de-shielding of protons. It causes shielding or de-shielding of protons. Example, benzene. Benzene is an example. You can see next one is van der Waals de-shielding. So van der Waals de-shielding. The electron cloud of a bulkier group. The electron cloud of a bulkier group will tend to repel. What happens? It will tend to repel the electron cloud surrounding the proton. So the electron cloud of a bulkier group will tend to repel the electron cloud surrounding the proton. So whenever there is a bulkier group which contains the electron cloud, it will repel the surrounding proton electron cloud. Okay, such a proton will be de-shielded. So that proton will be de-shielded and will resonate at slightly higher values. Okay, it will resonate at slightly higher values of delta than expected in the absence of this effect. So as the electron of bulkier group will repel the electron cloud of proton, this proton will be de-shielded and will resonate at slightly higher value of delta in the absence of this effect. So in the absence of this effect, this is de-shielded. Okay, that is the van der Waals de-shielding. Effect of temperature. resonance position of most signal is little affected by temperature. So resonance position of the signals will be affected by this temperature. Effect of solvent. Effect of solvent, if you see, chemical shift. Chemical shift change when the solvent change from carbon tetrachloride CdCl3 is COCl3. This is chemical shift changes when the change from CCl4 to CCl3. So this is CCl3 is 0.1 ppm. Okay, parts per million. So, but change to more polar solvents like methanol, the change is 0.3 ppm. So, if it changes to polar solvents like methanol, then what happens? The change will be around 0.3 ppm. When it is changing from CCl4 to CCl3, it will be 0.1 ppm. Solvents used in NMR are CCl4, CS2, CdCl3, COC, C6, D6, D2. These are the solvents which are used in the NMR. Okay, hydrogen bond, hydrogen bonding which affects the chemical shift. So what is the, this is one of the factor which affect the chemical shift. So this is this we will see hydrogen bonding. Protons that are involved in hydrogen bonding. Protons which are involved in hydrogen bonding are typically change the chemical shift value. So the protons which are involved in hydrogen bonding will be change the chemical shift values. Okay, the more hydrogen bonding, the more proton is deshielded, and chemical shift value is higher. As the hydrogen bonding is more, there will be more proton. Okay, is deshielded. When the hydrogen bonds are more, there will be deshielding of protons is also more. Then the chemical shift value is also higher. Okay, they are directly proportional to each other. So factors affecting factor effect on shift. You can see here sample temperature, a field shift, weakening of hydrogen bond. When the temperature increases, the field shift will occur and the weakening of hydrogen bonding occurs and deshielding of protons decreases. Solute concentration, downfield shift here. It is downfield shift or deshielding, we will say, when the solute concentration, uh, the effect of the solute concentration. Intramolecular hydrogen bond. So intramolecular hydrogen bond, excuse me, intramolecular hydrogen bond also affects the chemical shift. How it affects chemical shift value independent of temperature and solute concentration. Examples are the salicylates. Okay, so these are the factors which affects the chemical shift. What are the factors we have discussed? Electronegative groups, magnetic anisotropy of or diamagnetic effect of pi bonds, hydrogen bonding, van der Waals shielding, effect of temperature, and effect of solvent. These are the 6 factors which affect the chemical shift. Okay. Next one is proton NMR. Proton NMR, PNMR. The most common for NMR is based on the hydrogen one, nucleus or proton. It can give information about the structure of any molecule containing hydrogen atoms. So this is the most common for the NMR. Okay, is based on what? Is based on hydrogen one, nucleus or proton. Okay, it can give the information about any structure of any molecule which contains hydrogen atoms. If any molecule which is containing hydrogen atom, if you want to find the structure of those molecules, we can use this PNMR. Okay, proton NMR. So here you can see example is ethanol. Ethanol is an example here. CH3, CH3, OH. So here one is hydrogen. This is uh, This is A is hydrogen here, C is hydrogen, and B is alcohol here. We can observe here A and C are having same peaks, right? So three types, that is CH2, CH3, this is OH, okay? Interpretation of NMR. You can see the interpretation of one HNMR here, hydrogen, one hydrogen, nuclear magnetic resonance spectra. Number of signals indicates how many different kinds of protons are present. This here number of signals indicates what? Indicates how many different kinds of protons are present. Position of signals. Position of signals indicates something about chemical shift, magnetic electronic environment of protons. Okay, shows that which indicates what? Something about chemical shift, magnetic environment of protons. So the number of signals indicates what? Different kinds of protons are present. Position of signals indicates something about chemical shift and magnetic environment of protons. Relative intensity of signals. Relative intensity of signals gives the proportion to number of protons present signals. Okay. So relative intensity signals gives what? It gives a proportional to number of protons present signals. Okay. Splitting of signals, spin-spin coupling, you can say. Splitting of signals indicates the number of nearby nuclei, usually protons. So the splitting of signals or spin-spin coupling indicates the number of nearby nuclei, usually protons. N plus 1 rule. N plus 1 rule. The multiplicity of signal is calculated by using N plus 1 rule. So here N plus 1 rule is what? The multiplicity of signal which can be calculated using. So multiplicity of signals can be calculated by using this rule, N plus 1 rule. This is one of the rules to predict the splitting of protons. This is one of the rules to predict the splitting of proton signals. This is considered by the nearby hydrogen nuclei. So splitting of proton signals can be predicted by using this rule, and this can be considered by the nearby hydrogen nuclei. By nearby hydrogen nuclei, we can predict this splitting of proton signals. Okay. Therefore, n is equals to small n is equals to number of protons in nearby nuclei. So this small n indicates in the n plus 1 rule, n indicates the number of protons in the nearby nucleus. Okay. Here hydrogen atom. Zero hydrogen atom as neighbor n plus 1 is equals to 0 plus 1, which is a singlet. We can say as this is zero hydrogen atom, as the protons are zero here, the hydrogen atom as neighbors n plus 1, that is 0 plus 1, and it will be in a singlet state. Okay. When one hydrogen, if you take the one hydrogen atom, the neighbor will be n plus 1, 1 plus 1, that there it is doublet. When there are two hydrogen atom, that is two protons. Okay. Protons in the nearby nuclei, if the two protons are there in nearby nuclei in hydrogen atom as neighbor, so n plus 1 is equals to 2 plus 1, that is triplet. You can observe when it is zero hydrogen, it is singlet. When it is one hydrogen, it is doublet. When it's two hydrogen atom, it is triplet. Okay. Next one is spin-spin coupling splitting. Spin-spin coupling splitting. Here, spin coupling means the interaction between spins of neighboring nuclei. We can observe spin coupling means what? The interaction between two nuclei. Otherwise, interaction between spin of the neighboring nuclei in a molecule may cause the splitting of NMR spectrum. So, NMR spectrum, NMR spectrum may occur due to the cause of uh, interaction of interaction of spins of the neighboring nucleons. Okay, so the splitting pattern is related to the number of equivalent hydrogen atoms at the nearby nucleus. So this splitting pattern, the splitting of this NMR is also related to what? Related to the number of equivalent hydrogen atoms. So it depends on the number of equivalent hydrogen atom at the nearby nucleus. If it has more number of nuclei, then the splitting may be more. When there is less number of new hydrogen atom nearby, the splitting may be less. You can take the example of ethyl acetate. You can take the example of ethyl acetate for the spin coupling. Okay. So this is the example you can observe here. So there are three hydrogens here, three hydrogens here. So there is another hydrogen. So you can see here splitting pattern. First one is singlet. Third one is equivalent protons. Three equivalent protons are there, not coupled to any neighboring protons. So here there are no coupling of these protons have happened here. So second one is here quartet. Is quartet. Two equivalent protons are there. Split 1:3:1:3, 3:1, because coupled to three hydrogens here. Coupled to three hydrogens at the two positions. It's coupled with three hydrogens at two positions. Okay. Third one is triplet. Third one is triplet. Three equivalent protons. So there are three equivalent protons split into 1:2:1. So because coupled to the two hydrogens at the three positions. Two hydrogens at the three positions. This is the spin-spin coupling or spin-spin coupling splitting. Okay. Rules for this spin-spin coupling. There are some rules to find this spin-spin coupling splitting. Here you can observe. So chemical equivalent protons do not show spin-spin coupling. Okay? Chemically, which are equivalent protons, do not show spin-spin coupling here, and only non-equivalent protons couple. So the non-equivalent protons will couple. Okay. So chemically equivalent protons do not show spin-spin coupling. Here you can see Hb couples with Hc. Hb is coupling with Hc. Okay. Hb and Ha do not couple because they are equivalent. Hb and Ha. So Hb and Ha do not couple because they are equivalent. So chemically equivalent protons do not couple, but and only non-equivalent protons will couple here. This is non-equivalent. Hb is non-equivalent to not Ha. Sorry, Hc. That's why these are coupling. And Hc and Hd do not couple because they are equivalent. And again, you can see here Hc and Hd are Hd also do not couple because they are equivalent. Okay, these are equivalent, and this here you can observe Hb and Hc are non-equivalent because you can see here three hydrogen, here two hydrogens, here two hydrogens. So Hg and Hc do not couple, and also Hb and Ha do not couple, but Hb and Hd can couple here. Okay, or Hc can be coupled. Hb and Hc can be, sorry, Hb and Hc can be coupled here. Protons on adjacent carbons normally will couple. Protons are adjacent carbons. This is one carbon, this is one carbon. Here can this carbon hydrogen, this proton can be coupled with this other carbon hydrogen. Okay. Protons separated by 4 or more bonds will not couple. If the protons are separated by 4 bonds, if the protons are separated by 4 bonds, there will not be any splitting or no bonds. Cannot see the coupling. You can see here there are no 4 bonds and these can be coupled or splitting can be observed. But here if you see 1, 2, 3, 4, 4 bonds are protons are separated by 4 bonds. So these are not usually observed. Splitting cannot be usually observed in this case. Okay. So origins of origins of signal splitting. These are the origins we can observe here. The origins of signal splitting patterns. Each arrow represents an HB nuclear spin orientation. So the origins of signal splitting patterns. Each each arrow will be represented in a HB nucleus or spin orientation. You can say. So here HA to HB, HB to HA, that is spin coupling can occur. Here one HB atom. Here you can see spin coupling, two equivalent HB atoms are there. Two equivalent HB atoms are there. Spin coupling, there are three equivalent HB atoms you can observe. So this is the 1:1, that is you can observe here splitting in signal of HA. Here you can observe splitting in signal of HA to HB, that is here it's one spin up, one spin down. Here when both the spins are high up and both the spins are low here. Here you can observe one spin up, one spin down, one spin up, one spin down. Here you can observe it 1:3:3:3:1. These are the ratios you can observe from this. Okay, measurement of splitting effect and the distance between the peaks. Between the peaks, the distance on the basis of this distance, you can see the splitting effect. Okay, this is the J actually. This is coupling constant. Useful in one NMR, one H NMR of complex structure. This will be useful. Coupling constant is useful. One H, one hydrogen NMR complex structure. This is the instrumentation you can see. Instrumentation of the NMR. So in the instrumentation, there will be sample tube, sample holder. These are the components which are observed in the instrument in the NMR spectroscopy. That is sample tube, permanent magnet, magnetic coil, sweep generator, radio frequency transmitter, radio frequency receiver it is. So this is so radio frequency receiver and readout system. This seven components are there in the instrumentation. You can observe. Sample tube is here. The sample tube is there. This is the sample tube. You can observe. In the tube, we will keep the sample. These are the permanent magnets. You can here see powerful electromagnet supermagnets are there. You can see the magnetic coil. This is the magnetic coil. You can observe. Sweep generator. There will be a sweep generator attached to this one. Radio frequency transmitter is there. This is the radio frequency transmitter. Input oscillator you can see. And radio frequency receiver is there. This is the radio frequency receiver. Readout system. This is the readout system which can be connected to the system, and we can see the result here. So, these are the seven components. We'll elaborate these seven components. Sample tube, sample holder, sample tube or sample holder. It should be chemically inert. How the tube must be? It must be chemically inert. It should not react with any sample. Okay, it must be chemically inert, durable and transparent to NMR radiation. It must be durable and also transparent to the NMR radiation. Generally, about 8.5 centimeter long. Generally, about 8.5 centimeter long and approximately 0.3 centimeter in diameter is employed. So this sample tube will be 8.5 centimeter long and 0.3 centimeter of diameter. This is the sample holder. You can observe that These are the sample holders. You can see sample probe. It's the device. It is it is the device that holds sample tube in position and is provided with an air-driven turbine for rotating the sample tube almost 100 revolution per minute. So the sample tube is holded by this sample tube or sample holder is placed in a sample probe. It is a device hold the sample tube. Sample tube is holded by the sample probe and it has some air-driven turbines. This contains air-driven turbines which will rotate that sample tube. So the sample tube is kept in an air-driven turbine of sample probe and it will be rotated or it will be revolved. There are 100 revolutions per minute. Can be 100 revolutions per minute. You can see the permanent magnets here. These are the permanent magnets. So permanent magnets, it provides homogeneous magnetic field at 60 to 100 megahertz. So permanent magnet, what it will do, it provides the homogeneous magnetic field at 60 to 100 megahertz. We can apply magnetic field of range from or magnetic field of range from 60 to 100 megahertz homogeneously throughout the sample. Okay. Magnetic coil, it induces magnetic field when current flow through them. So it induces magnetic field when current flow through them. So when the current is flowing through this magnetic field, so there will be induced magnetic field coming from inside. So when current flows through this magnetic coil, there will be magnetic field generator or induced. Sweep generator next one. To produce equal amount of magnetic field pass through the sample. So sweep generator, what it does, it produces a equal amount of magnetic field when it passes through sample. Okay. Radio frequency transmitter. This is the radio frequency transmitter we can see here. This is the observer receiver. This is the radio frequency transmitter. This is the sample tube. This is the transmitting coils. These are the permanent magnets and observing coil. You can see. Transmitter. What does this transmitter radio frequency transmitter do? Let us see. Transmitter is fed onto a pair of coils. It is fed onto a pair of coils mounted on right angles. These are mounted on right angles here. You can see right angles to the path of field. To the path of field, they are mounted. 60 megahertz capacity is normally used. So mostly they use 60 megahertz capacity. Okay. Radio frequency receiver. Next one is radio frequency receiver. Detect radio frequencies emitted as nuclei relax at lower energy levels. What does this radio frequency receiver do? Detects the radio frequencies emitted as nuclei relax at lower energy level. Okay. Signal detector and recording system. So signal detector and recording system is the next one. So electrical signals generated is amplified by means of amplifier and then recorded. So after the radio frequency receiver, what happens? Radio frequency receiver detects the radio frequencies emitted as a nuclei relax at lower energy levels. So that is taken to the signal generator and recording system. The electrical signal will be generated and is amplified by means of amplifier. So it is amplified by means of amplifier and then recorded. There will be low signals which can be amplified and which can be recorded in the recording system. Okay. This is about the instrumentation. You can see the applications of this NMR spectroscopy here. Let us see the applications. Applications, one hydrogen NMR used for the structural elucidation of organic and inorganic solids. So one HNMR, what it does, how we will use this one HNMR is used for the structural elucidation of organic and inorganic solids. Okay, we can find the structures of organic and inorganic solids of by using this 1H NMR. Determines the physical and chemical properties of atoms. We can determine the physical and chemical properties of the atoms by using this NMR. Application in medicine. So anatomical imaging can be done. Measuring physiological function can be done. Flow measurement and angiography can be made by using this NMR. Tissue perfusion studies can be done. Tumors can be cured. MRI can be done. By using this NMR spectroscopy, MRI, magnetic radiation is given. By using that, you can see the pictures of whole body. So this MRI, tumors, tissue perfusion studies, flow measurement, angiography, and also measuring physiological function, and also analytical imaging can be used in the medical applications. Okay, so some other applications are there in the study of molecule can be used in the understanding of molecular structure and dynamics. As just now I said that it is used to study the structure of molecules both in solutions in solids. Okay, and molecular dynamics. NMR can be used to study the movement and interaction of molecules, including conformational changes, diffusion, and phase transitions. This can be used for the interaction of molecules also. Interaction of molecules can be done, including conformational changes, diffusion, and phase transitions. Okay. Material science is also used in the material science. It helps to characterize the structure and properties of various materials. So we can study the structure and properties of various materials using this NMR spectroscopy. Various materials including polymers, ceramics, and nanoparticles. By using this NMR, we can study the structure and properties of this polymers, ceramics, and nanoparticles. Next one is magnetic resonance imaging. Medical imaging, just now we have said. So a medical imaging technique is based on the principle of NMR spectroscopy. So based on the NMR spectroscopy only, this magnetic resonance imaging is done. So non-invasive imaging. MRI allows for detailed visualization of internal organs and tissues without the need of surgery or radiation exposure. So this gives the detailed visualization of internal organs without any radiation. Okay, magnetic resonance imaging. Diagnosis and sorry, diagnosis and monitor. MRI is used to diagnose a wide range of diseases, monitoring treatment effectiveness, and uh, access the health of various organs and tissues. Okay, by using this MRI, we can diagnose various of diseases, monitor treatment effectiveness, and access the health areas of organs and tissues. Okay. So there are some other applications are there. In the environmental monitoring also we will use. NMR can be used to analyze pollutants and contaminants in air, water, and soil samples. You can observe the pollutants which are present in air, water, and soil samples by using food science. NMR helps in food quality control, research, and analysis of food components. Okay, used in the quality control also. Material science and engineering. It is also used in material science and engineering. NMR is used to study the properties and structures of various materials, including polymers, ceramics, and nanomaterials. Okay. Earth's field, NMR and magnetometers. Here, NMR techniques are used to measure the strength and direction of Earth's magnetic field. Process control. NMR can be used to monitor and control chemical reactions and industrial process. Environmental metabolomics. NMR helps to study how environmental contaminants alter the metabolic profile of organisms. It can also be used in the environmental metabolomics. Okay. Also, process control can be done by using this NMR. Next topic will be the ESR spectroscopy. Just now we have completed the NMR spectroscopy. Now we are going into the ESR spectroscopy. We will see the brief explanation of this ESR spectroscopy. What is ESR spectroscopy and what is the principle behind this ESR spectroscopy? So here, this ESR spectroscopy is also known as the electroparamagnetic resonance. So ESR spectroscopy, electron spin resonance spectroscopy is also called as electron paramagnetic resonance spectroscopy or electron magnetic resonance spectroscopy. So ESR, EPR, EMR, these are not different, but they are same. Okay, ESR electron spin resonance, electron paramagnetic resonance, electron magnetic resonance. These are all same. Okay? The molecule which contains unpaired electrons are paramagnetic species or fluid radical species discovered by Zavorsky in 1944. So the molecules, if the molecules which are containing the unpaired electrons, if there are unpaired electrons in a molecule, if you observe, those are paramagnetic species. You can say that they are paramagnetic substance or species. It is a non-destructive technique. This ESR, EPR, EMR is a non-destructive technique. This cannot be destructive. And this is not a destructive. What is it? ESR actually? Let's see. It is a branch of absorption spectroscopy. Just now we have seen the NMR spectroscopy. NMR spectroscopy is also an absorption spectroscopy, isn't it? So here ESR spectroscopy is also an absorption spectroscopy in which radiation having frequency in microwave region. Radiation having frequency in microwave region, 300 megahertz to 300 gigahertz. So this is the microwave range is absorbed by paramagnetic substance. So in this ESR spectroscopy, what happens? There will be absorption spectroscopy. This is the absorption spectroscopy. So here a frequency ranges from the it has a frequency from in a microwave region, that is 300 megahertz to 300 gigahertz, and this will be absorbed by the sample. Okay, the sample is nothing but a paramagnetic substance to induce transition between magnetic energy levels of electron with unpaired spin. So this microwave region is absorbed by the paramagnetic substance to induce transitions. Okay, transition between the magnetic energy levels. Okay, magnetic energy levels of electrons with unpaired spin. Magnetic energy splitting is done by applying a static magnetic field. So this magnetic energy splitting is done by applying a static magnetic field. We will apply the magnetic field so that the splitting of magnetic energy is done. ESR phenomenon atoms having an odd electrons. So odd number of electrons can show the ESR phenomena. The atoms which are having the odd number of electrons, they can be in those can be we can see the ESR phenomena. Ions having partially filled inner electron shells. The ions which have partially filled electrons also shows the ESR phenomenon. Molecules that carry angular moment of electronic origin. Molecules that carry angular momentum also shows angular momentum of electronic origin also shows the ESR phenomenon. Free radicals having unpaired electrons also shows the ESR phenomenon. Molecules with unpaired electrons and zero magnetic field. Molecules which are unpaired, which have unpaired electrons and zero magnetic field. So those are also shows the ESR phenomenon. So ESR phenomena is shown by these atoms which are having odd number of electrons, which are partially filled inner shells, and which carry the molecules which carry the angular momentum, and also free radicals having unpaired electrons, and also paired electrons which are on the zero magnetic field. Molecules with paired electrons and zero magnetic field. Okay. So the ESR. Next one is principle of ESR. On what principle this ESR works? Let us see. Here, ESR is based on the absorption of microwave radiation by an unpaired electron when it is exposed to a strong magnetic field. So this will be as we have read out in the previous slide, that it is the absorption spectroscopy, isn't it? So whenever a sample is based on, it is based on the absorption of microwave radiation. This spectroscopy is based on what? Microwave radiation. When an unpaired electron, when by an unpaired electron, when it is exposed to strong magnetic field. When it is exposed to strong magnetic field, you can observe that absorption of microwave radiation can happen. Okay. On this principle, this is the principle of ESR. The electron energy levels of the atom or molecule will split into different levels. So the electron energy levels will be split into different levels. The magnitude of splitting is dependent on strength of applied magnetic field. So the magnitude of splitting will be done dependent on the strength of applied magnetic field. The atoms or molecules can be excited from one split level to another in the presence of an external radiation of frequency. So the atoms can be excited from one split level to another in the presence of external radiation of frequency. So whenever they give external radiation, there will be excitation of or splitting of splitting may occur of these atoms from one level to another level, corresponding to the frequency obtained from the difference in energy, difference between energy between the split levels. Okay, such excitation is called thus. Such type of excitation is called magnetic resonance absorption. When atoms or molecules are excited from one split level to another split level in presence of external radiation, what happens? There will be corresponding energy will be there, that will be changes between the split levels. There will be difference in energy between the split levels. Such type of excitation by absorbing the radiation is called a magnetic resonance absorption. Okay? The magnetic resonance frequency will hence be influenced by the local environment of the atom or molecule. So the magnetic resonance frequency will hence be influenced by the local environment of the atom or molecule. What causes the energy levels? What causes the energy levels? Let's see here. When spin is off, when spin is minus off. So the energy will be split into minus of, resulting energy levels in electron and magnetic field. Okay, this is the results levels, energy levels of electron. Describing the energy levels. Based upon the spin of electron and its associated magnetic moment, energy levels can be described on basis of based on the spin of electron and associated magnetic moment. Okay. For a molecule with one unpaired electron, molecule which contains one unpaired electron, the presence of magnetic field, the two electron spin energy levels are given by. So in the presence of magnetic field, the two electron spin energy levels can be given. Capital E is equals to GMB B naught MS. Here G is proportionality factor. MS is electron spin quantum number. MS is what? MS is electron spin quantum number. GMB is Bohr magneton, and B naught is the magnetic field. For a molecule with unpaired electron, the presence of magnetic field, two electron spin energy levels are given by. The two electron spin energy levels are given by using this formula, that is E is equals to G MB D naught MS. Okay. Hyperpoint splitting. You can see the hyperpoint splitting here. You can observe magnetic resonance can occur without an external magnetic field from interaction of the electron and nucleus fields. Such resonance produces fine and hyperfine structure of atomic spectra. Without the external magnetic field also, uh, there may be magnetic resonance occurs, but such type of resonance is called the fine and hyperfine structure of atomic spectra. The nuclei of atoms in a molecule or complex often have magnetic moments, which produces a local magnetic field at the electron. The interaction between an unpaired electron and a nuclei with non-zero nuclear spin is called a hyperfine interaction. The nuclei of atoms in a molecule or complex often have magnetic moment, which contains a magnetic moment, produces what? Local magnetic field at the electron. The interaction between the unpaired electron and a nuclei with no non-zero nuclear spin is called a hyperfine interaction. This leads to the splitting of ESR line and is known as a hyperfine spectrum. This is the hyperfine interaction we can observe here. So M is equals to plus of M is equals to minus of ML is equals to MI is equals to so R is equals to minus of, where we can observe the interaction with single nucleus of spin. This is the instrumentation. This is the schematic diagram of ESR spectrometer. We can observe here. There are some parts like klystron power, microwave stabilizer, frequency counter, power supply, field counter, loss meter, multimeter, lock-in amplifier, and crystal detector, isolator, variable attenuator, isolator. There are magnets and cavity, and also modulation cells. You can observe reference link will be there. So Hall probes are also there. So this is the schematic diagram of ESR. This is the hyperfine structure, and this is about the ESR, electron spin resonance, or electron paramagnetic resonance, or electron magnetic resonance spectroscopy. Okay, so by this I will end this class. Thank you.